Today we're going to continue with our theoretical discussion of how well we can learn a hypothesis class on a particular data set. So the setup that we're going to use is nothing new. We're going to have samples with data x and labels y. And we have a hypothesis class that maps our data into the label set. And we're still going to care about the training error that says how often on our training set we got the answer right or not. But we're going to change a little bit how we compute that. So what we're going to do is we're going to use the same training error definition as a starting point, but we're going to rewrite it a little bit. So the first thing that we can do is we can take apart this expectation looking thing here over an indicator function and explicitly write out that indicator function. What does that mean? And so what it means is that the indicator function returns 1 if the hypothesis answer doesn't match the truth. And so we can write that down explicitly, and there are 4 cases where it either matches or it doesn't. And so with a little bit of algebra, we can rewrite that as a product between the true answer, yi, and whatever our hypothesis spat out, h of xi. And so think through the various options of the label and the answer. And so if the answer was right, then this product will be 1. And if this product is 1, this whole thing will be 0. So that's if it got it right. But if they disagree, then the result of this will be -1. So you get 1 minus -1 over 2, which is 2 over 2, which is 1. And so that gives us this result here. So with a little bit of algebra, we've rewritten our expectation and our indicator function in this way. And so we can do a little bit more and factor out the 1/2. And once we do that, we get 1/2 minus 1 over 2m times this thing over here, which looks a lot like a correlation between the predictions and the labels. And so basically what you want from a good hypothesis class is good correlation with the true answers. And so an alternative to minimizing the training error is maximizing the correlation between the true labels y and the output of your hypothesis class. So this is a search over h's in our hypothesis class. So let's play around with this a little bit more and replace the true labels with something called Rademacher random variables. And you can think of these like flipping a coin. And with probability 1/2, the coin comes up +1. And with probability 1/2, the coin comes up -1. And so if we plug in the Rademacher random variables in place of the y's, this gives us a quantity known as the empirical Rademacher correlation. And this is basically saying that if you have a random answer instead of the truth, what's the best that a classifier could do? And notice that we're still using expectation here. And so this is an expectation over the random variable sigma, which is basically this coin flip, where the sigma here can be plus or minus 1. And so given whatever expectation, whatever coin flips you get, you're looking for the hypothesis that does the best at matching those random coin flips. Also note that this is the empirical Rademacher complexity with respect to a particular sample S. And so the xi's are coming from this sample S. And we'll make this a little bit more general in a second. This is another way of measuring the complexity of a hypothesis class. So last time we talked about the number of hypotheses in a hypothesis class as being a measure of how complex it is. This is another alternative measure. And so let's think about this a little bit more. What are the maximum or extreme values of Rademacher correlation? And if you think about this a little bit, you should be able to figure out that for a set of data that has m examples, you can have the extreme values of Rademacher correlation if your hypothesis class has only one hypothesis in it, or if it has 2 to the m hypotheses in it. So let's go over the simplest case first. So if you only have one hypothesis, we plug in the definition of Rademacher complexity. But notice that this max doesn't really make sense anymore because there's only one of them. So this max can go away. And once the max goes away and h is basically a constant, then we can factor it out. And so h now can go outside of the expectation since it doesn't depend on what sigma is. And so once we do that, then we have this expectation inside here. But this expectation is the expectation over things either being +1 or -1, so this expectation is just going to be 0. So that means that if you have a very simple hypothesis class, then you're only going to have a few ways of randomly aligning with random data, and so your Rademacher correlation is going to be near 0. Now let's take a look at the opposite side, where you have a very complex hypothesis set. And if you have 2 to the m hypotheses to choose from, you can basically set your bits however you want to align with whatever random noise you have. And so in that case, this becomes a little bit more complicated. So now we have to think about what's going on in here. And so think about this like a game. And so the universe gives you a sigma that is basically set randomly. And it's set randomly, but you get to choose a hypothesis set given the random setting of the sigmas, and you're trying to maximize this value. But you can do that perfectly because for any possible setting of sigma, you can choose how the hypothesis is going to set the answer for the input of xi. So you can make sure that this is always 1. And so, if that's the case, then this just becomes a sum over m1s. And so that means that you're going to have m over m, which is 1. So that is the maximum value that the Rademacher correlation can take on. If your hypothesis class is sufficiently complex, you can match just about anything you want and match the sigmas with whatever h you want to output so you get a perfect answer. Okay, so the Rademacher correlation is larger for more complicated hypothesis spaces. This basically says, what if you're just right for stupid reasons, that you're not actually learning anything from the data, you're just matching noise? And you don't want that to happen. You want to be able to be robust in the face of noise when you're trying to do machine learning. The nice thing about this notion is that it gives us generalization bounds. And we can use the same intuition to talk about all sets of a particular size. And so we'll define the Rademacher complexity with subscript m to be the expectation over all data sets of size m and their empirical Rademacher complexity. So this gives us a little bit more generalization. We can talk about a data distribution rather than talking about an individual set. Okay, so now that we've defined this more general notion of Rademacher complexity, we can start talking about convergence bounds. And so we'll eventually use these to talk about the error of machine learning algorithms, but for the moment we're going to take a slightly more general approach and talk about arbitrary functions f, where f maps inputs z to something between 0 and 1. In this case, we'll use f as a surrogate for the accuracy of a hypothesis. It's mathematically convenient and will show the complete connection in a little bit. But for the moment, what you can do is you can think about how far will the true error be away from our estimate on some data set S based on the complexity of our underlying hypothesis class and based on the number of samples that we've seen. And so this should look very familiar from our discussion of probabilistically approximately correct algorithms. It has the same flavor, but it's a little bit more general. And we'll see in the rest of today how we can apply these same intuitions for geometric definitions of hypotheses. So this will be a very useful tool that we'll be using a lot. One tool that we'll need is something called McDiarmid's inequality. And so this inequality says that if you have a function and you perturb one element of the vector that the function takes as input, that will be bounded by some amount ci, where the ci can be specific to the index of the vector. Now, we won't actually be using the index specificity here, so we'll just use functions that are bounded. If you change any one component of the function, it won't move by too much. And so McDiarmid's inequality says that if this is true, that perturbing one element in this vector doesn't change the overall function evaluation too much, then the probability of you moving by more than epsilon in expectation is going to be less than this value here, a function of how much the expectation moves, and how much changing any particular element will move the whole thing. Any perturbation of an individual element doesn't move it too much, the whole thing won't change. And the bigger epsilon is, the lower the probability that this inequality will be violated. We won't prove this here. It's proved in the book. It requires some math called martingale theory, basically constructing a sequence of these variables vk, conditioning on more and more of the inputs to the vector, showing that as you add more conditioning, it doesn't move too much. Okay, so why are we talking about McDiarmid's inequality? We want some function not to move too much, and the function that we don't want to move too much we'll define as this phi here. And this phi is basically saying, given our family of functions f, how much will the true accuracy deviate from our empirical measurements? And we'll explicitly write out the empirical average here. And so this is a function that will plug into McDiarmid's inequality. The first step in our proof is that we'll show that with probability at least 1 minus delta, phi is less than or equal to the expectation of phi on a sample plus some fudge factor. And we can get that by just plugging into McDiarmid's inequality, with epsilon being this, and Ci being 1 over m. Ci is 1 over m because if you change any Zi in your training set, that basically turns one answer from either being wrong to right or vice versa. So it can affect the total accuracy by at most 1 over m. So that's an easy way to apply McDiarmid's inequality, and we chose epsilon in this way so that the math works out nicely, and then we get this probability 1 minus delta here. Okay, so the next step is figuring out what this expectation over all sets S actually looks like. Take some sample S that we started with, and we're going to create a ghost sample of the same size as our original sample S. And we're going to ask how much can these two samples from the same distribution vary. Rewrite the expectation over data distribution in this sort of funky way that will say that the expectation of the value of our function f is equal to the empirical distribution of some explicit set S prime, and we'll take the expectation over all sets of S prime. So this is an argument that we've seen before. We used this last week in our discussion of pack learnability. You should be able to believe that if you take the expectation of a finite set over all finite sets, then that will be the true expectation of that quantity. Now we can extend the expectation of S prime over here. This is because this is S, and it doesn't depend on S prime. So it can move within the expectation for S prime. We can now add in an inequality. If you're taking a supremum of an expectation, you can get rid of the expectation because the supremum of the argument to the expectation is going to be larger than the expectation because you can think about the expectation as an average. So this gets rid of one of our expectations, and so now we have a nice difference of two expectations. 1 over a set S prime and 1 over a set S, each coming from the same distribution. And so now we need to figure out how much can these two sets differ. We'll create two new sets, T and T prime, by basically swapping elements between S and S prime with probability 0.5. This doesn't change anything, it's just a little bit of bookkeeping. S and S prime both came from the same data distribution, and that's also true for T and T prime. So they're identically distributed, and thus their difference is identically distributed. They're still basically the same thing. And so let's introduce a coin flip sigma I that says whether we flipped an element between S and S prime or not. So with probability 0.5, you don't swap, and with probability 0.5, you do swap. And so now we can compute the difference between T and T prime using this definition. And so this is basically a bunch of evaluations of our function f. At this point, you should be reminded of the title of today's lecture, Rademacher complexity. So this looks very much like our Rademacher complexities that we had before. We just have these coin flips with probability 0.5 embodied in a variable sigma. And the sigma takes on values plus or minus 1, saying whether we flipped it or not. And so the sigma I is controlling whether the direction of this difference gets flipped or not. And now we have rewritten the expectation in a way that adds an additional variable sigma. And so it doesn't seem like we've gotten very far yet, but this additional bookkeeping will be useful in a second. We had this expectation over S prime, and sigma, and now what we're going to do is we're going to take the supremum jointly. And so instead of taking the supremum over both s and s prime, what we're going to do is we're going to take the supremum over s prime and s individually. And this must be greater than the original supremum because each one is now free to be larger. They can't cancel each other out like they could before. And now what we're going to do is use linearity of expectations to break this up into two parts. But now we have two things that look exactly alike. So on this side, we have something that depends on s and s prime, but there are no elements from s in the set, so we can get rid of that expectation here. And here, we don't have anything that depends on s prime, so we can get rid of that expectation here. We can also get rid of this minus sign here because the sigmas are symmetric about 0 and random. So negative sigma I is exactly the same thing as sigma I because sigma I is plus minus 1 with probability 0.5. So given that, we now have two things that look exactly like our definition of Rademacher complexity over the same set. A set of size m drawn from our data distribution. Okay, so that's the final step, and hopefully you haven't gotten lost, and you'll remember each of these components as we put them together into our final proof. The first step was using McDiarmid's inequality to write out this inequality in terms of the expectation. And we defined phi in such a way that it was the difference between the true expectation and the empirical expectation on a particular set. So this is just the definition of phi. If we drop the sup, this is still true. In the second step, we rewrote the expectation over all sets S as a difference between two sets S and S prime. And we created this ghost set that treated these as Rademacher-looking variables, which we used some algebra to turn into exactly two Rademacher complexities. And so finally, we can plug in our empirical definition of Rademacher complexity and apply McDiarmid's inequality again to bound our empirical Rademacher complexity. And putting the two together, we now have something of the form that we want. The true expectation bounded by our empirical expectation plus the Rademacher complexity of our class of functions plus some fudge factor that depends on the probability that we want this to be true and the size of our data. But thus far, we've been talking about these z's. So what are these z's? So these z's you can think of as a combination, a Cartesian product of our data x and our labels plus minus 1. And the function applied to x and y is going to basically be an indicator function that says, did we get it right or not? Did the output of our hypothesis match the label or not? And so this now becomes our family of functions that we were talking about before in very general terms. And this quite easily leads to expressions for generalization and empirical error. You can have generalization if you take x and y distributed over your whole data distribution, and you can have the empirical error just taking the expectation on a particular set. So if we use this as our definition of f and z as the Cartesian product of x and y, you can plug this into our theorem, and then you get these nice generalization bounds. So we have replaced these expectations with what we actually care about, the generalization error, the empirical error, and the complexity of our hypothesis class as measured by Rademacher complexity. Next up, what we're going to do is try to see how the error bounds that we used Rademacher complexity to develop can actually be applied to classifier setups and hypothesis classes that we actually care about. So here are some nice guarantees if we know the Rademacher complexity for a hypothesis. But is there a relationship with simpler combinatorial measures? The answer to that is yes. And so the Rademacher complexity is very closely associated with something called the growth function that basically counts up for a particular set of M examples. How many ways can a hypothesis be applied to that set of examples? You can think about this as a number of ways that M points can be classified using a hypothesis family H. And there's a really straightforward connection to the Rademacher complexity if you take the Rademacher complexity of a class of functions taking values +1 or -1, i.e. a binary classifier. The growth function is useful because it plays a key role in what's called the Vapnik-Chervoninkas dimension. So that's Vapnik on the left and Chervoninkas on the right. They created a way of characterizing the complexity of hypothesis classes in terms of what's called the VC dimension. And the VC dimension is the largest example size that can be fully shattered by a classifier. That is, that no matter how you have labels assigned to those examples, your classifier will be able to recreate that labeling. This is another way of expressing the complexity of a hypothesis class. And so what we're going to be doing is proving the VC dimension for various classes of hypotheses. First, you need a lower bound and an upper bound. And so the lower bound is just showing an example of a set of a particular size that can be shattered by your hypothesis set. And then your upper bound is to prove that no set of d+1 points can be shattered by H. And that proves that your hypothesis class has VC dimension D. Okay, so let's start off. What's the VC dimension of hypotheses that are of the form of the interval from A to B? You should remember that this is the same form that we used for our Californian temperature hypothesis. What is the largest set that can be shattered by this hypothesis? Well, it's fairly clear that 2 points can be shattered. So if you have 2 points, then if they're both positive, you can completely enclose them by the interval. If neither is positive, just put the interval off to the side. If one of them is positive and the other is not, just put the interval around the positive one. Okay, so that shows us that 2 points can be shattered by this hypothesis class. We know the VC dimension is greater than or equal to 2, but is it greater than or equal to 3? It turns out not to be. You can prove that any 3 points cannot be shattered. For 3 points, no matter where they are on the number line, so long as they're distinct, there will be a middle point. And the middle point can never take on a negative if the other 2 points on the extremes are positive. So no set of 3 points can be shattered. That means that the VC dimension is 2 if your hypothesis set is closed intervals on the real line. Let's take, as an example, another hypothesis class that classifies points on a line as being either above or below a sine wave. parameterized by the frequency, omega. So can you shatter 3 points? Yes, you can. And here's a proof by picture. How about 4 points? You can also shatter 4 points, and the question is, how many points can you shatter? Is there a limit? It turns out, and you'll do this as a homework assignment, that the VC dimension of a sign on a line is infinite. For any set of size m, you can choose a frequency omega so that you classify all of your points perfectly. This means that the sine function probably isn't a very good classifier. It's way too complicated and can easily overfit on a training set. So the VC dimension obviously somehow tells you how complex a hypothesis class is, but what we want to do is to be able to prove generalization bounds. So let's go through how we can use VC dimension to talk about the growth function. If we have a hypothesis set with VC dimension D, then for all data set sizes m, then the growth function is going to be less than or equal to this combinatorial expression. And this is good because if you expand this combinatorial expression, you'll get some polynomial of the form m to the d. We'll then be able to use this expression in our generalization bounds. Okay, so we'll prove this, but first we need to go through some preliminaries. So the first thing is basically the definition of some combinatorial identities. If you remember Pascal's triangle from middle school, that basically gives you the binomial coefficients. If you're looking up a higher coefficient, you can just look at a lower order polynomial and add those together to get a particular binomial coefficient. The other thing that we'll do is, for various degenerate cases, we'll assume that if you're out of bounds, the answer is 0. This is fairly reasonable, and it makes the math a little bit easier. So to prove the statement about the relationship between the VC dimension and the growth function, we'll proceed by induction on m and d together. And our base cases are fairly obvious. If you have no data, then you can't really label the data, so we'll just say that there's only one labeling possible. And if your VC dimension is 0, you can't shatter even a single point, then your hypothesis set must be a fixed function, so in that case, the growth function still has to be 1. Okay, so now let's assume that our statement holds for all m prime and d prime less than m plus d. And so we're given our hypothesis set, that our sample size is m, and that the VC dimension of our hypothesis set is d. So what we're going to do is, from our original hypothesis space, which worked on m examples, we're now going to break this into 2 subspaces. And the way that we're going to break our original hypothesis space into 2 subspaces is take the original hypothesis set and only consider the first m minus 1 points, h1 and h2. And so how do you break up your original hypothesis space? Look at all of the hypotheses And we're going to need to put them into different sets depending on how they classify the mth example. We'll take a look at prefixes over the first m-1 examples. And so here are two cases where we have hypotheses in our original hypothesis set that look the same on the first m-1 examples, but give different answers on the final one, the mth example. And so whenever that happens, we need to create two new hypotheses, one that lives in H1 and one that lives in H2. If we have an mth example that is consistent with all of the previous m-1 examples, we only need to create one entry. It can go arbitrarily either in big H1 or in big H2. So this could have gone here or here, but we'll just put it here for the sake of simplicity. Here's another case where we have disagreement. Here we need to create a new hypothesis to live in H1 and a new hypothesis to live in H2. And so now we have the same representational power as our original hypothesis space, because we now have two separate spaces that basically encodes the difference between the first endpoints. So now we're going to use our inductive hypothesis. The size of H1 is this, and the size of H2 is this. And what we want to do is to show that this is going to be, once we add them together, of size m choose I, summed up to d. So the first thing that we'll do is we're going to rewrite the second expression as I minus 1, because we want the limits of the summation to be the same as our first sum. So we want d minus 1 to match d. So we'll rewrite this sum as going from I equals 0 to d, but we'll just change the indices to I minus 1 because we'll add this m minus 1 choose minus 1, which will be 0 and thus doesn't contribute to the sum. So once we've done that, we can now put both of these terms inside the same sum, apply Pascal's triangle to rewrite this as a single combinatorial expression. We've done it. We have proved what we wanted to prove. We have successfully applied induction. The other thing that you'll want to verify is that the combinatorial expression really is a polynomial of the form m to the d. This is some fairly simple algebra. I won't go through it, but you should be relatively sure of this. So we can combine our previous generalization results with Sauer's lemma, the thing we just proved, and apply our Rademacher complexity bounds. So we now have that the generalization error is going to be less than or equal to our empirical error plus a function of the complexity of our hypothesis class, the amount of data that we have, how certain we want to be, and again, the amount of data that we have. So that's great. We have the theory down. I realize this has been a more math-intense lecture than we've had in the past. Now that we have this theory down, we're going to look for algorithms that have good VC dimension and have good generalization results. and that work well in practice. And so we'll be talking next about a class of algorithms developed by Vladimir Vatnik, the V and VC dimension, that works very well in practice, support vector machines, and is a mainstay of machine learning. We'll work through how they work and why the theory says that they should work. So come to class with your questions, and we'll work through examples of Rademacher complexity and finding the VC dimension of various hypothesis classes. See you then.